We will now try to write the Schrodinger wave equation in different forms. In the previous class, we discussed about how to arrive at this form of Schrodinger wave equation. We will continue from here and try to write this Schrodinger wave equation in different forms. What we will do in the first step is we will take psi, the wave function psi, as the common term in the first three. Okay, so you can write it as dou square by dou x square plus dou square by dou y square plus dou square by dou z square of psi. Okay, we have removed this wave function psi as a common factor of from all the three terms plus 8 pi square m divided by h square into e minus v into psi is equal to 0. What is this term? This is a well-known operator called as Laplacian operator. This is nothing but the Laplacian operator in 3 dimension, which is represented as del square. So this term can be simply written as del square psi plus 8 pi square m divided by h square into e minus v into psi is equal to 0. This is another way of writing the Schrodinger wave equation. So this is a three-dimensional Schrodinger wave equation. This is also a three-dimensional Schrodinger wave equation written in different forms. There is one more way of writing this Schrodinger wave equation. What we will do is multiply equation 14 by h square by 8 pi square term. So we are multiplying the entire equation by this term h square by 8 pi square m. So when I multiply, what happens to the first term? First term becomes h square by 8 pi square m into del square psi. Okay, because I am multiplying by h square by 8 pi square m plus here I have 8 pi square m by h square. Okay, when it is multiplied by this term, you can see that they are reciprocal of each other, so they cancel and become 1. So plus e minus v into psi is equal to 0. Okay, which can be written as h square divided by 8 pi square m into del square psi plus e into psi minus v into psi is equal to 0, or e into psi is equal to, let us take the other two terms to RHS, becomes minus h square divided by 8 pi square m into del square psi plus v into psi. Okay, I will just interchange the RHS and LHS of this equation. It becomes minus h square divided by 8 pi square m into del square psi plus v into psi is equal to e into psi. Now here again we can remove psi as a common factor and write minus h square divided by 8 pi square m into del square plus v of psi is equal to e into psi. This term, okay, represents an operator called Hamiltonian operator H, and this operator called as Hamiltonian operator is a very important operator in quantum mechanics. Therefore this equation can be written as H of psi is equal to e into psi. This is another way of writing Schrodinger wave equation. Okay, Schrodinger wave. This is also Schrodinger wave equation 13, equation 14, or you can also use this, or you can also use equation 15. All represents the Schrodinger wave equation written in different forms. Okay, what is H? Let us write what is H here, where H is called as Hamiltonian operator, it is given by the expression h is equal to minus h square divided by 8 pi square m into del square plus v. Okay, it is a Hamiltonian operator in 3 dimensions. This is called as Hamiltonian operator. Remember, if you look at this very simple version of the Schrodinger wave equation, which is read as h of psi is equal to E into psi. It is not h into psi. I read it as h of psi because h is not a number or a function, it is an operator. So h of psi is equal to E into psi. We cannot cancel out psi on both the sides and say h is equal to E. We cannot do that because here in the RHS E is a simple number, energy, simple number which gets multiplied with psi, but in the RHS h is not a simple number, it is an operator that is operated on the function. So we cannot cancel psi and simply write h is equal to E. So this is the one of the very important and a simple version of Schrodinger wave equation. So equation 13 or equation 14 or equation 15, they are all 3-dimensional Schrodinger wave equation where h represents this term called as Hamiltonian operator. It is sum of two terms, minus h square by 8 pi square m into del square, which is a Laplacian operator, plus a potential energy operator. This potential energy is a simple multiplication operator. Okay, it is a simple multiplication operator. That what is multiplication operator, that we have discussed when we discussed about concept of operators. Now let us try to write what would be the corresponding Schrodinger wave equation in one dimension. So let us look at equation 13 and try to write the corresponding one-dimensional Schrodinger wave equation. What would be the corresponding one-dimensional Schrodinger wave equation? So how to reduce this three-dimensional equation to one-dimensional equations? Okay, in three-dimensional equation you have three variables x, y, z. In one dimension we require only one variable x. So these two terms becomes negligible, or they become zero in fact. So you have only one term with respect to x. That is one change you have to make. The second change you have to make is, here this wave function psi depends on three variables x, y, z. Now because it is a one dimension, the wave function psi should depend only on one variable x. So we have to make two changes. Replace psi of xyz by psi of x, and these two terms containing y are now disappearing. So the corresponding one-dimensional Schrodinger wave equation can be written as d square psi of x divided by dx square. That is first term. Here instead of partial derivative, again I am using ordinary derivative because there is only one variable. So this becomes d square psi of x by dx square. See here, psi is replaced by psi of x. These two terms are now not in the one-dimensional equation, plus 8 pi square m divided by h square into e minus b into psi of x is equal to 0. So this is a one-dimensional Schrodinger wave equation. So if we are dealing with a one-dimensional problem or a one-dimensional system, we can use one-dimensional Schrodinger wave equation. Suppose we are dealing with a two-dimensional problem, we have to write a two-dimensional Schrodinger wave equation, or else if it is a three-dimensional system, we have to use this general three-dimensional Schrodinger wave equation, and they are all time-independent Schrodinger wave equation. Now this is about one-dimensional Schrodinger wave equation. Let me concentrate again on equation 15. This is a very interesting result. I already told you in the last video lecture, maybe video lecture number 6, where we discussed about Eigen Function and Eigen Value. What do you mean by Eigen Function? If a function is operated by an operator, or if an operator A is applied on the function, if the same function is obtained back multiplied by a constant, then that function is called as an Eigen Function and the constant is called as an Eigen Value. So operator A applied on the function f of x, it gives the same function f of x again multiplied by a constant. Then this function is called Eigen Function, and the constant is called as eigen value. Now if we look at this simple version of Schrodinger wave equation, which I will write it here again, h of psi is equal to E into psi. So when this function is operated by the Hamiltonian operator, it gives the same function back but multiplied by a constant. So Schrodinger wave equation is nothing but an example for eigenvalue equation. So Schrodinger wave equation is an eigenvalue equation or eigenvalue problem for energy. Okay, why? Because when we apply the Hamiltonian operator on a wave function psi, we get energy as the eigenvalue. So in quantum mechanics, how do we calculate energy of the system? We calculate the energy of the system by applying an operator called Hamiltonian operator. So Hamiltonian operator corresponds to energy. When we apply an Hamiltonian operator on a wave function, it gives energy. And interesting to note that, okay, this Hamiltonian operator is an Hermitian operator. How? That will not go and prove it. Okay, let us take that result as granted. Okay, so this Hamiltonian operator is an Hermitian operator, and one of the important property of Hermitian operator is the eigenvalue of an Hermitian operator is always real. This operator may be complex or real, the wave function may be also complex or real, but the eigenvalue is always real. That is a important property of Hermitian operator. And why should we get a real value? Because this eigenvalue now, which is energy, represents the value of a physical quantity, and the value of any physical quantity should always be a real number. So that is why I stressed that point, that the eigenvalue of an Hermitian operator is always real. Now we really understand why it is real, or why we desire it to be a real number, because that eigenvalue represents the energy in this particular case, which is always a real number. So remember, Schrodinger wave equation is an operator equation. It is also called as an eigenvalue equation or eigenvalue problem representing energy. Okay, so now we will focus a bit more on this Hamiltonian operator. It is a very important operator in quantum mechanics. It is a linear operator as well as it is a Hermitian operator. Let me write this equation again. Okay, so in 3 dimension, Hamiltonian operator is given by the expression h is equal to minus h square by 8 pi square m into del square plus v. So this is the 3-dimensional Hamiltonian operator. Okay, del square is the Laplacian operator, v is the potential energy operator, which is a simple multiplication operator. Now you can write this expression even in 1 dimension, because we use this 3-dimensional equation only when we are dealing with a 3-dimensional problem. But suppose if we are dealing with a 1-dimensional problem, then we have to use 1-dimensional Schrodinger wave equation, and in that case we have to use the corresponding 1-dimensional Hamiltonian operator. So how can you write the Hamiltonian operator in 1 dimension? In 1 dimension it is written as minus h square by 8 pi square m. Remember, this Laplacian operator contains 3 terms: dou square by dou x square plus dou square by dou y square plus dou square by dou z square. But for 1 dimension we have the term d square by dx square only plus v. Actually we write it as v of x because the potential energy only depends on the x position of the particle. Here the potential energy depends on x, y, z, that is the position of the particle in space in 3 dimension, whereas it is the position of the particle only along x axis. So this is the corresponding 1-dimensional Hamiltonian operator. And this Hamiltonian operator H represents an operator for total energy. This is very important. Why Hamiltonian operator is an important operator in quantum mechanics? Because it represents the total energy of the particle. Why? If you look at this Schrodinger wave equation, I already told you, when the Hamiltonian operator is applied on a wave function, it gives the energy as the eigen value. That is the reason why Hamiltonian operator is an operator for calculating energy. That is, Hamiltonian operator represents an operator for calculating total energy. And since energy is a very important physical quantity of any system, and as a chemist, our top priority, okay, is to calculate the energy of a system, especially chemical system, because the energy of that system decides the stability and the reactivity of an atom or molecule. So for a chemist, energy is a very important quantity, and therefore this Hamiltonian operator has very much significance in chemistry problems because it represents an operator for energy. Now if you look at this expression, three-dimensional or one-dimensional expression for operator, this operator, Hamiltonian operator, contains two terms, first term plus second term, and this Hamiltonian operator nothing but represents the total energy. In fact, if you remember, the total energy also contains two terms. It is a sum of kinetic energy of the particle plus potential energy of the particle. So let me write the Hamiltonian operator again. H is equal to minus h square by 8 pi square m into del square plus v of x, y, z. This is the three-dimensional expression, or you can write h is equal to minus h square divided by 8 pi square m into d square by dx square plus v of x is the corresponding one-dimensional expression. This is the expression for operators. Now we will write an expression for the value of a physical quantity. Energy, the total energy E is nothing but sum of kinetic energy plus potential energy. So if you compare these two expressions with this, these two are the operators equations. This is a simple expression containing physical quantities. Okay, so if you logically compare, LHS is Hamiltonian operator in the first two term, and in the third term you have energy, which is nothing but the energy is nothing but corresponds to Hamiltonian operator. Hamiltonian operator corresponds to energy, or energy corresponds to Hamiltonian operator. I already told you Hamiltonian operator represents energy. And in the right hand side there are two terms in each of this equation, and the second term in all the three, if you see, this is a potential energy operator, this is also potential energy operator, and you have value of potential energy. So the second operator, there is a correspondence between the operator and the physical quantity. This is a potential energy operator, this is the corresponding value of potential energy. So the only left that we have to see is the first term. So by similar argument you can conclude that, okay, these term are nothing but the operators for kinetic energy. ಯಾಕಂದ್ರೆ LHS ನೋಡಿದ್ರೆ ಇಲ್ಲಿ Hamiltonian operator ಇದೆ, ಇಲ್ಲಿ total energy ಇದೆ. They correspond with one another. Hamiltonian operator represents energy. ಅದೇ ರೀತಿ in the second term you have potential energy operator. Here also you have potential energy. So this is the potential energy operator corresponding to this term, that is potential energy. So in ಉಳ್ಕೊಂಡಿರೋದು ಕೂಡ ಮ್ಯಾಚ್ ಆಗಲೇಬೇಕು. ಸೊ ಇಲ್ಲಿ potential kinetic energy ಇದೆ, ಆದ್ದರಿಂದ ಈ ಟರ್ಮ್ ಏನನ್ನು ರೆಪ್ರೆಸೆಂಟ್ ಮಾಡಬೇಕು? ದಿಸ್ ಟರ್ಮ್ ಇಸ್ ನಥಿಂಗ್ ಬಟ್ an operator corresponding to kinetic energy. This term is also an operator corresponding to kinetic energy. Therefore the expression for kinetic energy operator is minus h square divided by 8 pi square m into del square. This is a three-dimensional operator. If it is in one dimension, it becomes kinetic energy operator is equal to minus h square divided by 8 pi square m into d square by dx square. So these are the expressions for an operator for calculating kinetic energy of a particle in quantum mechanics. So if I apply Hamiltonian operator on a wave function, we get the corresponding energy. Similarly, if I apply this kinetic energy operator on the wave function, then we get the kinetic energy. So what we are observing is, okay, that we will generalize later. For each physical quantity, there is a corresponding operator in quantum mechanics. For example, if I want to calculate the energy, what should we do? We should apply the Hamiltonian operator on the wave function. If you want to calculate the kinetic energy, then we have to apply the kinetic energy operator on the wave function. If we generalize this, suppose if I want to calculate the momentum or the angular momentum of the particle, then we have to apply the momentum operator or the angular momentum operator on the wave function. Then we can find out what is the momentum or the angular momentum of the particle. Okay, we will discuss about these things in much greater detail when we discuss about postulate of quantum mechanics. So in the next class we will discuss some more important facts about Schrodinger wave equation. What is the physical significance of Schrodinger wave equation? What is the physical significance of wave function psi? Okay, and also we will understand what is the meaning of square of the wave function psi square. And finally we will also discuss about an important condition called as normalization condition. Remember, we defined a well-behaved function as a function which is finite, single valued, continuous and normalized, but we haven't defined what is normalized function. So we will in the next class mathematically define what do we mean by a normalization condition and why this normalization condition is very important. Then we will go to either I will discuss postulate of quantum mechanics first, or I will go through it. If possible, instead of discussing postulate of quantum mechanics, I will directly go to the application of Schrodinger wave equation. Different applications we have, such as application to particle in a one-dimensional box, application to a rigid rotator, application to a simple harmonic oscillator, so on. After that we may discuss the postulate of quantum mechanics.